Have you ever wondered what it would be like to stand on Earth 250 million years ago, when our planet looked nothing like it does today? Instead of 7 separate continents scattered across vast oceans, there was just one massive landmass stretching from pole to pole, surrounded by a single, enormous ocean that covered most of the planet. This wasn't science fiction. This was Earth during the age of Pangea, and it was unlike anything we could imagine today. Right now, as you're watching this video, you're sitting on a continent that was once part of something extraordinary. Every mountain range, every desert, every forest around you was once connected in ways that would completely reshape how we think about our planet's history. Tonight we're going back in time to explore what might be the most fascinating period in Earth's geological story, when our world operated under completely different rules. Welcome back to another journey through deep time. I'm so grateful you've chosen to spend your evening with me as we explore these incredible mysteries from our planet's past. Before we dive into tonight's adventure, I'd love to know where you're watching from and what time it is in your corner of the world. I'd also be incredibly grateful if you gave this video a like and perhaps subscribed. Now sit back and relax. The story begins now. Here's what makes tonight's story particularly mind-bending. We're not just talking about a different arrangement of continents. We're talking about a world where the very concept of weather, climate, and life itself operated on principles so extreme they challenge everything we understand about how planets work. This is the story of Earth's most ambitious geological experiment, and the results were both spectacular and terrifying. The story begins around 335 million years ago, during what geologists call the early Carboniferous period. But this wasn't a quick event that happened overnight. No, the formation of Pangia was a slow-motion collision that unfolded over tens of millions of years, driven by forces so powerful they could move entire continents like pieces on a cosmic chessboard. Imagine standing in space, watching Earth from above, as these massive land masses began their inexorable dance toward each other. In the north, there was Laurasia, a continental mass that included what we now know as North America, Greenland, Europe, and Northern Asia. In the south, Gondwana stretched across the southern hemisphere, containing the future South America, Africa, Antarctica, Australia, and India. These weren't just chunks of rock drifting aimlessly through ancient seas. They were massive continental plates being pushed and pulled by convection currents deep within Earth's mantle, forces so immense they make our most powerful earthquakes look like gentle tremors. The collision, when it finally happened, was nothing short of catastrophic. Picture 2 cosmic-sized freight trains moving toward each other at geological speeds, carrying the entire surface history of our planet. When Gondwana, Laurasia, and several smaller land masses finally smashed together around 320 million years ago, the impact created mountain ranges so massive they dwarfed anything we see today. These weren't ordinary mountains. The central Pangean mountains, formed by this continental collision, reached heights comparable to the modern Himalayas and stretched like a massive spine through the heart of the supercontinent. These peaks rose during the Carboniferous period and reached their maximum height during the early Permian, around 295 million years ago. Imagine a mountain range that made the Rockies, the Alps, and the Andes look like gentle hills running for thousands of miles through the center of a continent that stretched from the Arctic to the Antarctic. But the mountains were just the beginning of Pangea's extraordinary geography. The name itself tells us something profound about how this supercontinent dominated our planet. Pangaea comes from ancient Greek, meaning all earth, and that name was remarkably accurate. This single landmass occupied roughly 1/3 of Earth's entire surface, while the rest of the planet was covered by a single, vast ocean called Panthalassa. Think about that for a moment. Today, we have Pacific, Atlantic, Indian, Arctic, and Southern Oceans, each with their own currents, temperatures, and weather patterns. But 250 million years ago, there was essentially just one ocean, and it was enormous beyond comprehension. Panthalassa stretched from horizon to horizon, a hemisphere-sized body of water that made our modern Pacific Ocean look like a lake. This wasn't just water. This was an oceanic system, so vast it could generate weather patterns and ocean currents, unlike anything our planet had ever seen before or has seen since. The shape of Pangia itself was bizarre by today's standards. Rather than being a neat, compact landmass, the supercontinent was shaped like a giant letter C, with the bulk of its mass stretching between Earth's northern and southern polar regions. Within the cradle of this C-shaped continent lay another body of water called the Tethys Ocean, a warm sea that would play a crucial role in determining the climate patterns across the entire supercontinent. This geographic arrangement created something that sounds almost impossible. A world where you could theoretically walk from the North Pole to the South Pole without ever getting your feet wet, crossing through every climate zone imaginable along the way. But here's where the story gets truly extraordinary. The climate patterns that emerged from this unusual geography were so extreme, they created some of the most inhospitable conditions Earth has ever experienced. The interior regions of Pangia became something like a continental-scale desert, but not just any desert. This was an arid zone so vast and so extreme that it likely represented one of the most extensive desert systems in Earth's entire geological history. Imagine the Sahara Desert, but instead of covering just a portion of northern Africa, picture it stretching across an area larger than all of modern Asia. The temperatures in these interior regions swung between extremes that would make Death Valley look temperate. Scorching hot days were followed by frigid nights, with temperature variations so severe they would have been nearly uninhabitable for most forms of life. But why were these interior regions so impossibly dry and extreme? The answer lies in something that seems almost too dramatic to be real: the Pangean mega monsoon. This wasn't just a regular monsoon system like we see in modern India or Southeast Asia. This was a planetary-scale weather pattern so powerful it controlled the climate of an entire supercontinent. Here's how this mega monsoon worked, and it's absolutely fascinating. During the Northern Hemisphere's summer, when Earth's axial tilt directed the most intense solar radiation toward the northern part of Pangaea, the massive landmass would heat up like a continental-scale oven. This created enormous areas of rising hot air and low pressure across what we now call North America, Europe, and Northern Asia. Meanwhile, the Southern Hemisphere remained relatively cooler. This temperature difference drove winds on a scale we can barely imagine today. Moisture-laden air from the surrounding oceans would rush toward the superheated northern regions, bringing massive amounts of precipitation to the coasts. But here's the critical part. By the time these weather systems reached the interior of the continent, thousands of miles from any ocean, they had dumped all their moisture. The result was that the heart of Pangaea became a rain shadow zone of truly epic proportions. Then during the Northern Hemisphere's winter, the entire system would reverse. The southern regions would heat up, and the winds would shift direction, carrying moisture toward Gondwana while leaving the northern regions in a state of extreme aridity. This created seasonal variations so intense that parts of Pangaea would swing between monsoon-like flooding and desert conditions within the span of a few months. The effects of this mega monsoon system were visible across the entire supercontinent. Geological evidence shows enormous seasonal variations in rock formation, with layers that record periods of intense flooding alternating with deposits that could only form in desert conditions. These weren't subtle changes. These were environmental swings so dramatic they left permanent signatures in the rock record that geologists can still read today, more than 250 million years later. But perhaps the most remarkable aspect of Pangaea's climate was how it changed over time. The supercontinent existed for an incredible 160 million years from its initial assembly, around 335 million years ago, until it began breaking apart around 175 million years ago. During this vast span of time, Earth's climate went through several distinct phases, each more extreme than anything we experience today. During the late Carboniferous period, when Pangia was still forming, much of the supercontinent was covered in vast swamp forests. These weren't ordinary swamps, they were continental-scale wetlands that would eventually become the coal deposits we mine today. Picture tropical rainforests stretching across areas the size of modern continents, filled with primitive trees and giant ferns, all thriving in a greenhouse climate that had no modern equivalent. But as Pangia reached its full extent during the Permian period, around 295 to 252 million years ago, the climate became increasingly extreme. The interior regions dried out even further, while the mega monsoon system reached its maximum intensity. Temperature differences between the equator and the poles became less pronounced than they are today, but the seasonal variations became so extreme they created what paleoclimatologists describe as the most continental climate in Earth's history. This was a world without polar ice caps, where even the Arctic and Antarctic regions remained unfrozen year-round. But paradoxically, it was also a world where vast interior regions experienced temperature swings that would have been lethal to most modern forms of life. Days in the interior deserts could reach temperatures that would make modern desert extremes seem mild, while nights would plunge to near freezing, even in tropical latitudes. The plant life that managed to survive in this harsh environment was unlike anything we see today. The giant swamp forests of the earlier Carboniferous period gave way to tougher, more resilient vegetation. Gymnosperms, the ancestors of modern conifers, began to dominate the landscape. These were plants that had evolved sophisticated water conservation strategies and could survive in the increasingly arid conditions. On the ground, carpets of moss, liverworts, and ferns created miniature ecosystems around the bases of primitive conifers, ginkgos, and palm-like cycads. But these plant communities were constantly under stress from the extreme seasonal variations and the general trend toward increasing aridity as Pangia matured. The animal life of this period was equally extraordinary and equally adapted to extreme conditions. This was the age of the synapsids, the mammal-like reptiles that dominated terrestrial ecosystems before the dinosaurs took over. These weren't small, insignificant creatures. Many synapsids were large, sophisticated predators and herbivores that had evolved complex social behaviors and advanced thermoregulation strategies. The most famous of these early synapsids was Dimetrodon, a formidable predator that looked like something from a science fiction movie. Despite its lizard-like appearance, Dimetrodon was actually more closely related to mammals than to reptiles, and its most distinctive feature, a large sail-like fin on its back, was probably used for temperature regulation in the extreme climate of Pangia. These animals had to cope with environmental conditions that would challenge even modern desert specialists. The seasonal temperature swings, the extreme aridity of the interior regions, and the unpredictable nature of the mega monsoon system created evolutionary pressures unlike anything life had faced before or has faced since. But all of this remarkable life, all of these extraordinary adaptations, all of the complex ecosystems that had evolved to thrive in Pangia's extreme conditions, were about to face the ultimate test. Around 252 million years ago, at the end of the Permian period, something happened that would change the course of life on Earth forever. The Great Dying was beginning, and it would be the most catastrophic extinction event in our planet's history. More than 95% of marine species would vanish. More than 70% of land animals would disappear. The world that had existed during the height of Pangia was about to end, but from its ashes would emerge something entirely new, the age of the dinosaurs. What caused this unprecedented catastrophe, and how did it reshape life on our ancient supercontinent? The answer involves volcanic eruptions so massive, they make modern volcanic disasters look like gentle hiccups, climate changes so severe they pushed Earth's systems to their breaking point, and a recovery process that would take millions of years to complete. The scale of what was about to unfold across Pangia defies easy comprehension. Imagine if every volcano on Earth today erupted simultaneously, and then multiply that catastrophe by a factor of hundreds. That still wouldn't capture the sheer magnitude of what began around 252 million years ago in what is now Siberia. The Siberian traps represent one of the most violent geological events in Earth's recorded history. These weren't ordinary volcanic eruptions, they were flood basalts, massive outpourings of lava that covered an area roughly 2/3 the size of the modern United States. The total volume of molten rock that poured across the landscape reached between 1 and 4 million cubic kilometers. To put that in perspective, that's enough lava to bury the entire continental United States under a layer of molten rock several hundred feet deep. But the lava itself was only the beginning of the catastrophe. The volcanic gases released during these eruptions fundamentally altered Earth's atmosphere and climate. Massive quantities of carbon dioxide, sulfur compounds, and other toxic gases billowed into the atmosphere, creating a greenhouse effect so intense it pushed global temperatures to levels that made Pangia's already extreme climate seem moderate by comparison. The timing of these eruptions was devastatingly precise. Recent research has shown that the Siberian flood basalts began at almost exactly the same moment as the Permian extinction event, providing compelling evidence that these volcanic outpourings were the primary trigger for the greatest mass extinction in Earth's history. Picture what this meant for the already stressed ecosystems of Pangia. The supercontinent's interior regions, which had been struggling with extreme aridity and temperature swings, suddenly faced conditions that were beyond the tolerance limits of virtually all terrestrial life. The carefully balanced plant communities that had taken millions of years to adapt to Pangia's harsh climate were overwhelmed by the rapid environmental changes. The effects rippled through every level of the ecosystem. The gymnosperm forests that had covered parts of the supercontinent began to die off as temperatures soared and acid rain, created by the volcanic sulfur compounds, poisoned the soil. The delicate balance that had allowed complex food webs to exist in Pangia's challenging environment collapsed within what may have been as little as 100,000 years, a blink of an eye in geological terms. The fossil evidence from this period tells a story of almost complete ecological collapse. Rock layers from the late Permian show abundant signs of diverse plant communities, with fossil remains of the conifer forests that had blanketed many regions of Pangia. But the early Triassic layers that follow tell a very different story. Instead of plant fossils, these rocks are dominated by the remains of fungi, organisms that thrived in the aftermath of the extinction as they fed on the vast quantities of decaying organic matter left behind by the environmental catastrophe. For the animal life of Pangia, the Great Dying represented an existential crisis unlike anything life on Earth had ever faced. The synapsids, those remarkable mammal-like reptiles that had dominated terrestrial ecosystems for millions of years, saw their numbers decimated. Dimetrodon and its relatives, the apex predators that had ruled Pangia's food webs, vanished from the fossil record. The large herbivorous synapsids that had grazed in the gymnosperm forests disappeared as well, leaving behind ecosystems that were almost completely empty of large terrestrial vertebrates. The marine ecosystems surrounding Pangia suffered even more catastrophic losses. The warm Tethys Ocean, which had harboured incredible diversity during the Permian period, became a biological wasteland. More than 95% of marine species went extinct, transforming the ocean from a vibrant ecosystem teeming with life into something approaching a sterile sea. But perhaps the most remarkable aspect of this catastrophe was what happened next. The end Permian extinction marked not just the end of one chapter in Earth's history, but the beginning of another. The Triassic period that followed would see life experiment with entirely new forms and strategies, ultimately giving rise to some of the most successful animals ever to walk the Earth. The early Triassic world was a desolate place. The first few million years after the extinction were characterized by what paleontologists call the coal gap, a period when virtually no coal deposits formed anywhere on Earth. This absence of coal reflects the near-complete collapse of terrestrial plant communities. Without thriving forests to create the organic matter that eventually becomes coal, the rock record from this period is remarkably barren of the carbon-rich deposits that characterize other geological eras. Estimates suggest it may have taken up to 10 million years for Earth's ecosystems to recover from the devastation of the Great Dying. That's a recovery period longer than the entire span of time since the extinction of the dinosaurs. During those long millennia, Pangia remained a largely empty stage, waiting for new actors to emerge and fill the ecological roles left vacant by the Permian extinction. The recovery, when it finally began, was unlike anything that had come before. The surviving plant species began to diversify and spread across Pangia's landscapes, but they did so in a world that had been fundamentally altered by the extinction event and the continuing effects of the massive volcanic eruptions. The climate remained extreme, but life began to adapt to these new conditions in innovative ways. As plant communities slowly re-established themselves, they created opportunities for animal life to return to terrestrial environments. But the animals that emerged from this recovery were different from their Permian predecessors. The synapsids, while not completely extinct, never regained their former dominance. Instead, a new group of reptiles began to diversify and experiment with new body plans and ecological strategies. These were the archosaurs, and they would become the ancestors of some of the most successful animals in Earth's history. During the early stages of the Triassic recovery, these archosaurs were small, relatively insignificant members of the recovering ecosystems. But they possessed certain advantages that would prove crucial in the changing world of post-extinction Pangaea. The climate during the Triassic period remained extreme by modern standards, but it was also remarkably stable compared to the chaotic conditions that had characterized the end Permian extinction. The absence of polar ice caps meant that temperature gradients from equator to pole were less extreme than they are today, creating a more homogeneous global climate. This stability, combined with the ecological opportunities created by the extinction, provided ideal conditions for evolutionary experimentation. Around 240 million years ago, something extraordinary appeared in the fossil record. These were small bipedal creatures with elongated hind limbs and relatively large brains for their body size. They moved with a distinctive gait, running on 2 legs rather than 4, and showed evidence of sophisticated behavioral adaptations. These were the first dinosaurs, and they were about to begin one of the most successful evolutionary radiations in Earth's history. The earliest dinosaurs were not the massive, imposing creatures that would later dominate Mesozoic ecosystems. Instead, they were relatively small, agile animals that probably weighed no more than a few dozen pounds. But what they lacked in size, they made up for in adaptability and intelligence. These early dinosaurs possessed several key advantages that allowed them to thrive in the recovering ecosystems of Triassic Pangaea. Their bipedal locomotion gave them speed and agility advantages over many of their contemporaries. Their relatively large brains allowed for sophisticated behavioral adaptations, including potentially complex social behaviors and advanced hunting strategies. Perhaps most importantly, their physiology was well suited to the extreme climate conditions that still characterized much of Pangaea during the Triassic period. One of the most successful early dinosaurs was Colaphysis, a slender predator that first appeared around 225 million years ago. Despite weighing only 40 to 50 pounds, Colaphysis was a formidable hunter, with sharp teeth, grasping claws, and hollow bones that gave it a lightweight build perfectly suited for quick, agile movement. The hollow bones, which give Calaphysis its name, meaning hollow form, were an innovation that would become characteristic of all later dinosaurs and would eventually allow some species to grow to enormous sizes while maintaining relatively efficient locomotion. Coelophysis and its relatives fed on a variety of prey, including small reptiles, early mammals, and possibly insects and other arthropods. Their hunting strategies were likely sophisticated, involving pack behavior and coordinated attacks on larger prey. Fossil evidence suggests that some early dinosaurs may have been capable of complex social interactions, with group living arrangements that provided advantages in both hunting and protection from predators. But dinosaurs weren't the only success story of the Triassic recovery. Around the same time that the first dinosaurs were establishing themselves in terrestrial ecosystems, another group of animals was quietly beginning its own evolutionary experiment. These were the first true mammals, tiny creatures that looked somewhat like modern shrews, but represented a completely new approach to vertebrate biology. The earliest mammals were small, perhaps no larger than a mouse, and they lived in the shadows of the larger reptiles that dominated Triassic ecosystems. But they possessed several revolutionary adaptations that would eventually prove crucial to their long-term success. They were warm-blooded, meaning they could maintain constant body temperatures regardless of environmental conditions. They had fur for insulation, allowing them to remain active during the cool nights that characterized even tropical regions of Pangia. Most remarkably, they produced milk to nourish their young, providing their offspring with nutritional and immunological advantages that would prove crucial in the competitive world of post-extinction recovery. One of the earliest known mammals was Eosostrodon, a creature about 3 feet long that still laid eggs like its reptilian ancestors, but fed its young with milk after they hatched. This combination of reptilian and mammalian characteristics provides a fascinating glimpse into the evolutionary transition that was occurring during the Triassic period. The coexistence of early dinosaurs and early mammals during the Triassic period set the stage for one of the most important ecological relationships in Earth's history. For the next 160 million years, these two groups would evolve alongside each other, with dinosaurs generally dominating the large-bodied terrestrial niches, while mammals remained primarily small, nocturnal, and specialized for ecological roles that didn't directly compete with their reptilian contemporaries. The plant communities that supported these recovering animal populations were also undergoing significant changes during the Triassic period. The gymnosperms that had survived the end Permian extinction began to diversify into new forms better adapted to the post-extinction world. Conifers became increasingly dominant in many regions, their water conservation adaptations serving them well in the still arid interior regions of Pangia. Alongside the conifers, other gymnosperm groups began to flourish. Cycads, with their palm-like appearance, became common in many tropical and subtropical regions. Ginkgos, represented today by only a single species, were diverse and widespread during the Triassic. These plant communities created the foundation for the complex food webs that would characterize the later Mesozoic era. The recovery of Triassic ecosystems was also marked by the return of complex marine life to the ocean surrounding Pangaea. The Tethys Ocean, which had been largely sterilized by the end Permian extinction, began to support new communities of marine reptiles, fish, and invertebrates. Some of these marine reptiles grew to enormous sizes, filling ecological niches that had been vacant since the extinction. As the Triassic period progressed and life continued to recover and diversify, the geological forces that had created Pangaea were beginning to change. The same tectonic processes that had brought the continents together were starting to pull them apart again. Deep beneath the supercontinent, new patterns of mantle convection were creating stresses that would eventually tear Pangia into fragments. The first signs of this breakup appeared around 200 million years ago, near the end of the Triassic period. Rift valleys began to form in what would eventually become the Atlantic Ocean, and volcanic activity increased along these developing fracture zones. The great experiment of Pangia was beginning to end, but its effects on life would continue to influence evolution for hundreds of millions of years to come. The legacy of Pangia extends far beyond its existence as a supercontinent. The extreme climate conditions, the massive extinction event, and the subsequent recovery fundamentally shaped the trajectory of life on Earth. The dinosaurs that emerged during the Triassic recovery would go on to dominate terrestrial ecosystems for more than 160 million years. The mammals that began their evolutionary journey in Pangia's shadows would eventually inherit the Earth after the dinosaurs' extinction. But perhaps most importantly, the story of Pangia demonstrates the incredible resilience and adaptability of life itself. Even in the face of the most catastrophic environmental changes our planet has ever experienced, life found ways not just to survive, but to innovate and diversify in directions that would have been impossible under more stable conditions. The story of how life responded to Pangia's extreme world reveals something profound about the creative power of evolutionary processes when pushed to their absolute limits. As we move deeper into the Triassic period, around 230 million years ago, the recovering ecosystems of Pangia were becoming increasingly complex and sophisticated. The early dinosaurs like Co-evolutionary were no longer alone in their ecological experiments. New species were appearing with remarkable frequency, each testing different solutions to the challenges of life on a supercontinent where environmental extremes remained the norm rather than the exception. One of the most fascinating aspects of this recovery was how different regions of Pangia began to develop their own distinct evolutionary trajectories. Remember, this was still a single landmass, but its sheer size meant that different areas experienced dramatically different climate conditions. The coastal regions, with their access to moderating oceanic influences and the moisture brought by the mega-monsoon systems, became laboratories for one type of evolutionary experimentation. Meanwhile, the harsh interior regions, still characterized by extreme temperature swings and persistent aridity, fostered entirely different evolutionary solutions. Along the coastlines, particularly those facing the warm Tethys Ocean, plant communities began to achieve levels of complexity that hadn't been seen since before the Great Dying. These weren't simply recovering versions of Permian ecosystems, they were something entirely new. The gymnosperms that form the backbone of these communities had evolved sophisticated strategies for dealing with the seasonal extremes of the mega-monsoon climate. Picture forests where the trees had developed specialized root systems that could rapidly absorb and store enormous quantities of water during the brief but intense monsoon seasons, then survive for months on these reserves during the dry periods. The leaves of these plants showed adaptations we rarely see in modern ecosystems, with some species capable of dramatically altering their surface area and water retention properties as seasons changed. These weren't subtle adjustments. These were plants that could essentially transform their entire physiology multiple times each year to cope with environmental swings that would kill most modern vegetation. The animal communities that developed in these coastal forests were equally remarkable. The early dinosaurs were diversifying rapidly, with new species appearing that showed increasingly sophisticated adaptations to their environment. Some lineages were experimenting with size increases, growing larger than their earlier relatives, but maintaining the agile bipedal locomotion that had made their ancestors successful. Others were exploring different dietary strategies, with some of the first herbivorous dinosaurs beginning to appear alongside the carnivorous forms. But perhaps most intriguingly, these early dinosaur communities were developing complex social behaviors that suggest levels of intelligence and cooperation rarely seen in modern reptiles. Fossil evidence from this period includes what appear to be communal nesting sites, group feeding areas, and even potential evidence of cooperative hunting strategies. These weren't simple-minded lizards stumbling through a hostile world. These were sophisticated animals with advanced behavioral repertoires that allowed them to thrive in conditions that would challenge even modern social mammals. The success of these early dinosaurs wasn't just a matter of individual adaptations. They were becoming ecosystem engineers, animals whose activities fundamentally altered their environments in ways that created new opportunities for other species. Their feeding behaviors affected plant community structure. Their nesting activities created disturbance patterns that influenced soil development and water retention. Their movement patterns established pathways that other animals could follow, creating the beginnings of the complex migration routes that would characterize later dinosaur ecosystems. Meanwhile, in the interior regions of Pangia, evolution was taking very different directions. The extreme conditions that characterized these vast continental interiors had created what paleontologists now recognize as some of the most specialized ecosystems in Earth's history. The plants that managed to survive in these regions had evolved water conservation strategies, so extreme they bordered on the impossible. Some of these interior plant communities developed what can only be described as underground economies. Extensive root networks connected individual plants across vast distances, allowing them to share water and nutrients during the harshest periods. Above ground, these plants might appear to be struggling individuals, barely clinging to life in the desert conditions. But below the surface, they were part of vast cooperative networks that could span hundreds of square miles. The animals that lived in these interior desert regions were equally specialized. Some of the most remarkable synapsids of the Triassic period evolved in these harsh environments, developing physiological adaptations that pushed the boundaries of what we thought was possible for land vertebrates. These creatures could survive temperature swings that ranged from over 140 degrees Fahrenheit during the day to near freezing at night. They had evolved specialized kidney systems that could extract water from food sources so efficiently they rarely needed to drink free water. But the most extraordinary aspect of these interior ecosystems wasn't their individual adaptations, it was their timing. Many of the animals that lived in Pangia's interior regions had evolved sophisticated biological clocks that allowed them to predict and prepare for the extreme seasonal changes brought by the mega-monsoon system. Months before the rains arrived, these animals would begin physiological changes that prepared them for the brief period of abundance. Similarly, they would begin preparing for the dry season while the monsoons were still active. This kind of long-term biological forecasting required neural capabilities that we rarely see in modern reptiles. It suggests that some of the animals living in Triassic Pangia had evolved cognitive abilities specifically adapted to dealing with extreme environmental predictability. They weren't just reacting to immediate environmental cues. They were anticipating future conditions and preparing for them in advance. As the Triassic period progressed, these regional differences in evolutionary strategy began to create something unprecedented in Earth's history. A single landmass supporting multiple parallel experiments in complex ecosystem development. Different parts of Pangia were essentially testing different solutions to the fundamental challenges of life on a supercontinent, and the results were spectacular in their diversity. The marine ecosystems surrounding Pangia were undergoing equally dramatic transformations. The oceans that had been largely sterilized by the Great Dying were not simply recovering their former diversity, they were experimenting with entirely new approaches to marine life. The marine reptiles that began to appear during the Triassic period were unlike anything that had existed in Permian seas. Some of these marine reptiles grew to sizes that rivaled modern whales, but they achieved these dimensions through completely different evolutionary pathways. Their body plans, their feeding strategies, and their reproductive behaviors all represented novel solutions to the challenges of large-scale marine life. The warm, relatively shallow seas that surrounded much of Pangia provided ideal conditions for these experiments in marine gigantism. The success of these marine reptile communities had important implications for life on land as well. Many of these oceanic giants were predators that could venture into coastal waters and even onto beaches to hunt. This created evolutionary pressure for terrestrial animals to develop new defensive strategies and behaviours. Some of the most sophisticated group behaviours seen in early dinosaur communities may have evolved in response to the threat posed by these marine superpredators. The interaction between marine and terrestrial ecosystems during the Triassic period was more complex and intimate than anything we see in modern environments. The extreme seasonal variations caused by the mega monsoon system meant that coastal regions experienced dramatic changes in sea level, salinity, and temperature throughout the year. Animals that lived in these transitional zones had to be equally comfortable in marine and terrestrial environments, leading to the evolution of some of the most versatile vertebrates in Earth's history. As we approach the middle of the Triassic period, around 240 million years ago, the evolutionary experiments that had begun during the post-extinction recovery were reaching new levels of sophistication and complexity. The early dinosaurs that had appeared as small, relatively simple predators were diversifying into an array of forms that foreshadowed the incredible variety that would characterize later dinosaur faunas. Some lineages were experimenting with herbivory, developing the specialized dental and digestive adaptations needed to process the tough, fibrous plant material that dominated Triassic vegetation. Others were growing larger and developing more sophisticated hunting strategies. Still others were exploring semi-aquatic lifestyles, taking advantage of the seasonal wetlands created by the mega monsoon system. But perhaps the most significant development during this period was the appearance of the first truly large dinosaurs. Plateosaurus, which appeared around 210 million years ago, reached lengths of nearly 30 feet and represented a quantum leap in dinosaur size and ecological impact. These weren't just scaled-up versions of earlier forms. They had evolved entirely new body plans and physiological systems that allowed them to achieve sizes that would have been impossible for their ancestors. The success of large herbivorous dinosaurs like Plateosaurus had cascading effects throughout Triassic ecosystems. Their feeding activities could strip vegetation from vast areas, creating disturbance patterns that influenced plant community succession. Their movements created pathways and clearings that other animals could exploit. Most importantly, they represented a new category of prey that could support larger and more sophisticated predators. The appearance of large herbivorous dinosaurs during the Middle Triassic also coincided with significant changes in plant community structure. The gymnosperms that had dominated early Triassic vegetation were being joined by new forms that were better adapted to the grazing pressure created by large herbivores. Some plants evolved chemical defenses, producing compounds that made them unpalatable or even toxic to herbivores. Others developed physical defenses, growing thicker bark, thorns, or other structures that could deter feeding. But perhaps most remarkably, some plant communities began to evolve what can only be described as cooperative relationships with herbivorous dinosaurs. Certain gymnosperm species appeared to benefit from moderate grazing pressure, which cleared competing vegetation and created ideal conditions for germination and growth. These plants began to produce fruits and seeds that were specifically adapted to be dispersed by dinosaurs, creating some of the first examples of sophisticated plant-animal mutualisms in terrestrial ecosystems. The complexity of these ecological relationships was reaching levels that hadn't existed before the Great Dying and wouldn't be seen again until much later in Earth's history. Different species weren't just coexisting in the same environments. They were developing intricate webs of interdependence that made entire ecosystems more resilient and productive than the sum of their individual parts. The success of these complex Triassic ecosystems was also creating new opportunities for the other major vertebrate groups that were sharing Pangia with the dinosaurs. The early mammals, still small and primarily nocturnal, were diversifying into an array of ecological niches that allowed them to coexist with their much larger reptilian contemporaries. Some were developing specialized diets, feeding on insects, seeds, or other food sources that weren't being exploited by dinosaurs. Others were exploring arboreal lifestyles, taking advantage of the increasingly complex forest canopies that were developing in coastal regions. The synapsids, though no longer the dominant large vertebrates they had been during the Permian, were far from extinct. Some lineages were evolving into highly specialized forms, adapted to specific environmental niches. These weren't evolutionary dead ends, struggling to survive in a dinosaur-dominated world. They were successful, sophisticated animals that had found ways to thrive alongside their archosaur competitors. The diversity and complexity of life during the Middle Triassic period represented something unprecedented in Earth's history. Never before had terrestrial ecosystems achieved such levels of organization and sophistication. The extreme conditions created by Pangia's unusual geography had pushed evolution to develop solutions that wouldn't have been necessary or possible under more moderate environmental conditions. But even as these complex ecosystems were reaching new heights of diversity and sophistication, the geological forces that had created Pangia were beginning to change. Deep beneath the supercontinent, new patterns of mantle convection were creating stresses that would eventually tear the landmass apart. The first signs of this impending breakup were becoming visible on the surface as volcanic activity increased and rift valleys began to form. The end of the Triassic period, around 201 million years ago, would bring another mass extinction event, though not as severe as the Great Dying that had ended the Permian. This Triassic-Jurassic extinction would eliminate many of the sophisticated ecosystems that had developed during the Middle Triassic, but it would also create new opportunities for the surviving groups to diversify and expand. The dinosaurs that survived this transition would go on to dominate the Jurassic and Cretaceous periods, achieving sizes and diversity that made their Triassic ancestors look modest by comparison. The mammals would continue their patient evolutionary experiment, remaining small but developing the advanced physiological and behavioral capabilities that would eventually allow them to inherit the Earth after the dinosaurs' extinction. But the legacy of Pangia extended far beyond the specific groups of animals that lived during its existence. The extreme environmental conditions, the massive extinction events, and the subsequent recoveries had fundamentally altered the trajectory of evolution on Earth. The innovations and adaptations that developed in response to Pangia's challenges would continue to influence life for hundreds of millions of years. The story of life on Pangia reveals something profound about the relationship between environmental challenge and evolutionary innovation. When conditions are stable and moderate, evolution tends to produce gradual refinements of existing solutions. But when environments become extreme and unpredictable, evolution responds with bursts of creativity that can fundamentally reshape the biological world. The supercontinent that had dominated our planet for 160 million years was beginning its final chapter, but the biological legacy of its extreme world would continue to unfold in ways that would ultimately lead to the incredible diversity of life we see today. The breaking apart of Pangaea would create new oceans, new climate patterns, and new opportunities for evolutionary experimentation, but it would do so using the biological toolkit that had been forged in the crucible of supercontinent extremes. As we prepare to witness the dramatic breakup of this ancient landmass and explore how its fragmentation would reshape our planet once again, we can appreciate that we're looking at one of the most important transitions in Earth's biological history. The world that would emerge from Pangea's dissolution would be fundamentally different from anything that had come before, but it would be built on the innovations and adaptations that had been tested and refined during the supercontinent's remarkable reign. The forces that would ultimately tear Pangaea apart were already stirring deep beneath the supercontinent's foundation during the late Triassic period. But these weren't sudden, catastrophic events that happened overnight. Instead, they represented the beginning of one of the most gradual yet transformative processes in Earth's geological history. A slow-motion dissolution that would unfold over tens of millions of years and completely reshape our planet's geography. Deep within Earth's mantle, the same convection currents that had originally brought the continental masses together were beginning to reorganize themselves. Picture enormous rivers of molten rock flowing through the planet's interior, driven by temperature differences that created circulation patterns thousands of miles across. These mantle currents had been responsible for pushing Gondwana and Laurasia together to form Pangaea, but now they were shifting direction, creating new upwelling zones that would eventually pull the supercontinent apart. The first signs of this impending breakup appeared as subtle changes in volcanic activity across different regions of Pangaea. Around 220 million years ago, during the late Triassic period, geologists can detect evidence of increased magmatic activity in areas that would eventually become the boundaries between separating continental fragments. These weren't the massive flood basalts that had caused the Great Dying at the end of the Permian. Instead, they were more localized volcanic events that created linear chains of eruptions, early indicators of the rift systems that would eventually split the supercontinent. The process began in what would become the Central Atlantic region, along a line that ran roughly between what we now recognize as Eastern North America and Northwestern Africa. Deep beneath this zone, rising columns of hot mantle material began to create bulges in the overlying crust. These thermal domes stretched and weakened the continental rock, creating the first hairline fractures that would eventually become the Atlantic Ocean basin. But the breakup of Pangaea wasn't simply a matter of the continent cracking apart like a piece of pottery. The process was far more complex and involved fundamental changes in the way Earth's tectonic system operated. As the supercontinent began to fracture, it created opportunities for new patterns of ocean circulation to develop. These changing oceanic currents would have profound effects on global climate patterns, potentially influencing the very evolutionary processes that were continuing to shape life across the landmass. The timing of Pangaea's initial breakup coincided with another significant extinction event, though not nearly as severe as the Great Dying that had ended the Permian period. The Triassic-Jurassic extinction event, which occurred around 201 million years ago, eliminated roughly 20% of marine families and had significant impacts on terrestrial ecosystems as well. While the exact cause of this extinction remains debated, many scientists believe it was related to the massive volcanic activity associated with the formation of the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. This volcanic activity was directly related to the early stages of Pangaea's breakup. As the continental crust began to stretch and thin along the developing rift zones, it created pathways for enormous quantities of magma to reach the surface. The resulting eruptions covered vast areas of what would become Eastern North America, Western Africa, and parts of South America, with layers of basaltic lava. The environmental effects of these eruptions, while severe, were more localized than the global catastrophe that had ended the Permian period. For the complex ecosystems that had developed during the Middle and Late Triassic period, this extinction event represented another major disruption, but also another opportunity for evolutionary innovation. Many of the sophisticated ecological relationships that had developed during the Triassic recovery were severed, but the surviving species found themselves in a world with new ecological niches to explore and exploit. The dinosaurs, which had already established themselves as successful and diverse components of Triassic ecosystems, were among the groups that weathered this extinction event relatively well. In fact, the Triassic-Jurassic extinction may have actually benefited dinosaur evolution by eliminating some of their competitors and opening up new ecological opportunities. Many of the advanced synapsid lineages that had coexisted with dinosaurs during the Triassic period were eliminated during this extinction, leaving dinosaurs as the dominant large terrestrial vertebrates for the first time. As Pangia entered the Jurassic period around 200 million years ago, the supercontinent was beginning to show clear signs of its impending fragmentation. The rift valleys that had begun forming during the late Triassic were deepening and widening, creating long, narrow basins that would eventually become ocean floors. But this process was still in its early stages, and most of Pangia remained connected as a single landmass. The climate during the early Jurassic period was significantly different from the extreme conditions that had characterized much of the Triassic. As the rift systems developed and the first narrow seaways began to form between separating continental fragments, they created new pathways for ocean water to penetrate into the interior regions of the supercontinent. This had a moderating effect on the extreme continental climate that had dominated Pangia during its peak extent. The mega monsoon system that had created such dramatic seasonal variations during the Triassic period began to weaken as the geography of the supercontinent changed. The development of rift valleys and early seaways created new sources of moisture for interior regions that had been almost completely arid during earlier periods. This climatic moderation had profound effects on both plant and animal communities across Pangia. Plant communities that had been restricted to coastal regions during the Triassic period began to expand into interior areas as conditions became more hospitable. The gymnosperm forests that had developed sophisticated adaptations to extreme aridity found themselves in a world where water stress was less severe and growing seasons were more predictable. This allowed for the development of more complex forest ecosystems with greater structural diversity and more extensive food webs. The changing climate also created new opportunities for animal communities to develop. The harsh interior regions that had supported only highly specialized desert-adapted species during the Triassic period became accessible to a broader range of organisms. Migration routes that had been impossible during the height of Pangia's aridity became viable, allowing for greater mixing of populations and accelerated evolutionary change. The dinosaurs that had survived the Triassic-Jurassic extinction began to diversify rapidly during the early Jurassic period. The reduced competition from other vertebrate groups, combined with the expanding range of habitable environments, created ideal conditions for dinosaur evolution. New lineages appeared that experimented with different body sizes, dietary strategies, and ecological roles. Some of the most significant developments during this period involved the evolution of the first truly gigantic dinosaurs. The sauropods, which would eventually become the largest land animals ever to exist, first appeared during the early Jurassic period. These weren't simply larger versions of earlier herbivorous dinosaurs. They represented fundamentally new approaches to vertebrate biology, with body plans and physiological systems that had no precedent in earlier terrestrial animals. The evolution of giant sauropods had cascading effects throughout Jurassic ecosystems. Their feeding activities could alter entire landscapes, creating clearings in forests and changing patterns of plant succession across vast areas. Their sheer size made them largely immune to predation once they reached adulthood, allowing them to exploit food resources that were unavailable to smaller herbivores. The success of giant herbivorous dinosaurs during the Jurassic period also drove the evolution of larger and more sophisticated predators. The first truly massive theropod dinosaurs appeared during this time, developing the size and strength necessary to potentially threaten even adult sauropods. These predator-prey relationships created some of the most dramatic ecological dynamics in Earth's history. But the most significant aspect of Jurassic dinosaur evolution wasn't just the evolution of gigantic forms. It was the incredible diversity of ecological strategies that different dinosaur lineages began to explore. Some groups became highly specialized for aquatic or semi-aquatic lifestyles, developing adaptations that allowed them to exploit the expanding network of rift valley lakes and early seaways. Others evolved sophisticated social behaviors, with evidence suggesting that some species lived in large herds with complex social structures. The plant communities of the Jurassic period were also undergoing significant changes in response to the evolving herbivore communities. The intense grazing pressure created by large dinosaur herds drove the evolution of new defensive strategies in plants. Some species developed chemical defenses so sophisticated they could adjust the toxicity of their tissues in response to herbivore pressure. Others evolved rapid growth strategies that allowed them to recover quickly from grazing damage. Perhaps most remarkably, some plant communities began to develop what can only be described as collaborative relationships with dinosaur herbivores. Certain conifer species appeared to benefit from moderate browsing pressure, which cleared competing vegetation and created ideal conditions for their seedlings. These plants began to produce cones and seeds that were specifically adapted for dispersal by large dinosaurs, creating some of the most sophisticated plant-animal partnerships in prehistoric ecosystems. The marine ecosystems surrounding the fragmenting supercontinent were experiencing equally dramatic changes. As the rift valleys deepened and began to flood with seawater, they created new marine environments that were unlike anything that had existed during Pangia's peak extent. These narrow, elongated seas had unique characteristics that fostered the evolution of specialized marine communities. The early Atlantic Ocean, which began forming along the rift between North America and Africa, was initially a much smaller and shallower sea than it would eventually become. But even in its earliest stages, it provided habitat for marine organisms that had been excluded from the massive Panthalassa Ocean by its sheer size and the extreme conditions along Pangia's coastlines. Marine reptiles that had survived the Triassic-Jurassic extinction began to diversify rapidly in these new marine environments. Some lineages evolved into forms that were perfectly adapted to the shallow, warm conditions of the early Atlantic. Others developed the ability to move between marine and freshwater environments, taking advantage of the complex network of rift valley lakes and rivers that connected the interior of the fragmenting supercontinent with the expanding ocean basins. The development of new seaways also had important implications for marine circulation patterns. As ocean water began to penetrate deeper into the continental interior through the developing rift systems, it created new pathways for heat and moisture transport. This had moderating effects on climate across much of Pangaea, contributing to the more hospitable conditions that characterized the Jurassic period. But perhaps the most significant consequence of Pangaea's early breakup was the way it began to isolate different continental fragments from each other. As the rift valleys widened and deepened, they created barriers to the movement of terrestrial organisms. Populations that had been connected across the supercontinent began to become isolated on separate continental fragments. This geographic isolation had profound evolutionary consequences. Species that had been part of continuous populations across Pangaea began to evolve independently on different continental fragments. Over time, this would lead to the development of distinct regional faunas and floras, each adapted to the specific conditions of their continental home. The process of continental drift that began with Pangaea's breakup would continue for millions of years, eventually creating the modern configuration of continents and oceans that we see today. But the biological consequences of this process began immediately, as populations became isolated and began evolving in different directions. The early stages of this isolation can be seen in the fossil record from different parts of the former supercontinent. Dinosaur species that appear in North American rocks from the Middle Jurassic period are increasingly different from contemporary species found in South America or Africa. This divergence reflects the early stages of the evolutionary separation that would eventually produce the distinct biogeographic regions we recognize today. The mammals that had survived the Triassic-Jurassic extinction also began to diversify during the Jurassic period, though they remained relatively small and ecologically limited compared to the dinosaurs. However, the changing environmental conditions created new opportunities for mammalian evolution. Some lineages began to explore arboreal niches in the increasingly complex forest ecosystems. Others developed semi-aquatic adaptations that allowed them to exploit the expanding network of freshwater environments. The success of small mammals during the Jurassic period was partly due to their ability to exploit ecological niches that were unavailable to larger dinosaurs. Their small size, high metabolic rates, and sophisticated sensory systems made them ideal for nocturnal lifestyles in environments where large dinosaurs were less active. This temporal partitioning allowed mammals and dinosaurs to coexist with minimal direct competition. As the Jurassic period progressed and Pangia continued its slow-motion breakup, the biological world was being fundamentally restructured in ways that would influence evolution for hundreds of millions of years. The extreme environmental conditions that had characterized the supercontinent during its peak extent were giving way to more moderate and diverse climate patterns. The ecosystems that had been adapted to continental-scale aridity were being replaced by more complex and diverse biological communities. The fragmentation process wasn't uniform across the supercontinent. Some regions separated quickly, with oceanic crust forming between continental fragments within a few million years. Other areas remained connected by land bridges for much longer, allowing continued biological exchange even as the overall supercontinent structure broke down. This complex pattern of separation and connection created a mosaic of evolutionary pressures across the former supercontinent. Some populations experienced rapid isolation and divergent evolution, while others maintained genetic connectivity for extended periods. The result was a complex pattern of biological diversification that would eventually produce the incredible variety of life forms that characterized the later Mesozoic era. The climate changes associated with Pangia's breakup also had important implications for ocean chemistry and atmospheric composition. As new ocean basins formed and marine circulation patterns changed, they altered the way carbon and other elements cycled through Earth's climate system. These changes contributed to the generally warm, ice-free conditions that characterized much of the Mesozoic era. The absence of polar ice caps during this period created climate conditions that were remarkably stable compared to more recent geological periods. Temperature gradients from equator to pole were less extreme than they are today, and seasonal variations were more moderate in most regions. This climatic stability provided ideal conditions for the evolution of the complex ecosystems that would characterize the later Jurassic and Cretaceous periods. But stability is a relative term when discussing geological timescales. While the Jurassic climate was more stable than the extreme conditions of Triassic Pangaea, it was still subject to significant variations driven by volcanic activity, changes in ocean circulation, and other factors. These variations provided the environmental pressures that continued to drive evolutionary change throughout the period. As we move deeper into the Jurassic period and witness the continuing fragmentation of Pangaea, we can see that we're observing one of the most important transitions in Earth's biological history. The supercontinent that had dominated our planet for more than 160 million years was giving way to a new world of separated continents and expanding oceans. The biological innovations that had been forged in the crucible of Pangaea's extreme conditions were now being tested in new environments and ecological contexts. The dinosaurs that had emerged from the Triassic recovery were beginning their golden age, diversifying into forms that would dominate terrestrial ecosystems for more than 100 million years. The mammals that had survived in the shadows of the reptilian giants were beginning their own patient evolutionary experiment, developing the physiological and behavioral capabilities that would eventually allow them to inherit the Earth. The plants that had learned to survive in Pangea's harsh continental interior were now spreading into new regions and developing new relationships with the evolving animal communities. The marine ecosystems that had been largely confined to the margins of the supercontinent were expanding into new ocean basins and experimenting with new forms of biological organization. The world that would emerge from Pangea's dissolution would be fundamentally different from the supercontinent that had preceded it, but it would be built on the biological foundation that had been established during the supercontinent's remarkable existence. The extreme conditions, the mass extinctions, the recoveries, and the evolutionary innovations of the Pangean era had created a biological toolkit that would prove remarkably versatile and successful in the changing world of the later Mesozoic. As the great supercontinent continued its inexorable journey toward fragmentation, life was preparing for its next great adventure. The separated continents would drift apart, carrying with them the seeds of biological diversity that would eventually blossom into the incredible variety of ecosystems that would characterize our planet's more recent geological history. But that transformation was still millions of years in the future, and the story of how life adapted to the breakup of Pangea was only just beginning. The transformation of Earth's biological landscape during Pangea's breakup wasn't just about the physical separation of continents. It was about the fundamental rewiring of evolutionary processes that had been shaped by 160 million years of supercontinent conditions. As we move into the Middle Jurassic period, around 170 million years ago, we begin to see something unprecedented in Earth's history: the simultaneous operation of multiple independent evolutionary experiments on what were becoming increasingly isolated continental fragments. Picture the scene as these early rifts widened into genuine seaways. The narrow Atlantic that was forming between North America and Africa wasn't yet the vast ocean we know today. It was more like an enormous inland sea, perhaps similar to the modern Mediterranean, but stretching for thousands of miles. This growing waterway created the first real barrier to terrestrial animal movement since Pangea's formation, and the biological consequences were immediate and profound. On the eastern side of this developing ocean, the dinosaur populations that would eventually become the European and African faunas began to diverge from their North American relatives. These weren't dramatic changes that happened overnight. Instead, they represented the beginning of subtle shifts in evolutionary pressure that would accumulate over millions of years. The slightly different climate conditions on each side of the widening seaway, the varying plant communities that developed in response to these conditions, and the gradual genetic isolation of populations all contributed to an accelerating pattern of biological divergence. The sauropod dinosaurs provide a fascinating window into this process. During the early Jurassic, these giants had been relatively uniform across Pangaea, with similar species found from what is now the American Southwest to the forests of ancient Africa. But as the Atlantic widened and populations became isolated, different lineages began experimenting with different solutions to the challenges of gigantism. In North America, some sauropod lineages developed increasingly sophisticated social behaviors, with evidence suggesting they lived in large herds that migrated across vast distances following seasonal food resources. These North American giants evolved relatively longer necks and more specialized feeding structures, adaptations that allowed them to exploit the tall conifer forests that were becoming increasingly common in the region's climate. Meanwhile, on the African side of the widening Atlantic, sauropod evolution took different directions. The slightly warmer, more stable climate conditions in this region favored the evolution of even larger body sizes, but with different proportions and feeding strategies. Some African lineages developed broader, more powerful bodies that allowed them to process tougher, more fibrous plant material. Others evolved more elongated builds that were optimized for reaching vegetation in the increasingly diverse forest canopies. These weren't just minor variations on a common theme. They represented the beginning of fundamental divergences that would eventually produce sauropod lineages so different they would be difficult to recognize as close relatives. The process of continental drift was essentially creating parallel universes of dinosaur evolution, each responding to slightly different environmental pressures and developing along unique evolutionary trajectories. The theropod dinosaurs, the carnivorous lineages that would eventually give rise to modern birds, were undergoing equally dramatic changes during this period. The isolation of populations on different continental fragments created opportunities for predator-prey arms races to develop independently in different regions. In some areas, the evolution of increasingly large herbivorous dinosaurs drove the development of massive predators capable of hunting them. In other regions, the abundance of smaller prey species favored the evolution of more agile, intelligent hunters. One of the most remarkable aspects of this period was the way different continental regions began to develop their own signature approaches to carnivorous dinosaur design. The theropods that were evolving in what would become North America were developing increasingly sophisticated pack hunting behaviors and advanced sensory capabilities. Some lineages were experimenting with early forms of the complex respiratory systems that would later make birds such efficient flyers. On other continental fragments, theropod evolution was exploring different possibilities. Some regions saw the development of theropods with increasingly powerful jaw muscles and teeth designed for crushing bone, adaptations that allowed them to exploit carcasses more efficiently. Others developed lineages with elongated skulls and necks, perfectly designed for fishing in the expanding network of Rift Valley lakes and early seaways. But perhaps the most significant development during this period wasn't related to the giant dinosaurs that tend to capture our imagination. It was the quiet evolutionary revolution that was occurring among the smaller, more agile dinosaur lineages that would eventually give rise to birds. These creatures were developing a suite of adaptations that would prove revolutionary: hollow bones for weight reduction, increasingly sophisticated feathers for insulation and display, and most importantly, the complex respiratory and circulatory systems that would eventually make powered flight possible. The earliest evidence of feathered dinosaurs appears in the fossil record during this Middle Jurassic period, and it's clear that these structures initially evolved for purposes other than flight. The feathers of these early dinosaurs were probably used for temperature regulation in the increasingly variable climate conditions created by Pangia's breakup. Some species may have also used elaborate feather displays for communication and mate selection, behaviors that were becoming increasingly important as populations became more scattered and isolated. The plant communities that formed the foundation of these evolving ecosystems were also undergoing dramatic changes in response to the shifting geography and climate. The gymnosperms that had dominated Pangia's vegetation during the Triassic period were being joined by new lineages that were better adapted to the more moderate, humid conditions developing in many regions. One of the most significant botanical developments during this period was the evolution of the first flowering plants, or angiosperms. These weren't the diverse, colourful flowers we associate with modern ecosystems. The earliest angiosperms were small, relatively simple plants that looked more like modern magnolias than roses or daisies. But they possessed a revolutionary innovation: enclosed seeds that were protected during development and could be dispersed more efficiently than the exposed seeds of gymnosperms. The appearance of flowering plants during the Middle Jurassic period represented one of the most important evolutionary innovations in the history of terrestrial life. These plants could reproduce more quickly and efficiently than their gymnosperm contemporaries, allowing them to colonize new habitats and respond more rapidly to environmental changes. More importantly, they began to develop complex relationships with animal pollinators, creating entirely new categories of ecological interaction. The early pollinators weren't bees or butterflies, which wouldn't evolve until much later. Instead, they were primitive beetles and other insects that were attracted to the protein-rich pollen and nectar produced by early flowering plants. These relationships weren't as sophisticated as modern plant-pollinator partnerships, but they represented the beginning of one of the most important co-evolutionary processes in Earth's history. The marine ecosystems surrounding the fragmenting supercontinent were experiencing equally revolutionary changes. As new ocean basins formed and existing seaways deepened, they created opportunities for marine life to experiment with ecological strategies that had been impossible during Pangea's peak extent. The relatively narrow, shallow seas that characterized the early stages of continental breakup had very different characteristics from the vast, deep Panthalassa Ocean that had surrounded the supercontinent. These new marine environments were warmer, more nutrient-rich, and more geographically complex than the open ocean. They provided ideal conditions for the evolution of diverse marine reptile communities that were adapted to specific local conditions, rather than the broad, generalized strategies that had been necessary for survival in Panthalassa. Some of the most spectacular marine reptiles in Earth's history evolved during this period. The plesiosaurs, long-necked marine reptiles that could reach lengths of over 40 feet, developed into apex predators that dominated the food webs of the expanding Atlantic and other early ocean basins. These weren't simply large aquatic lizards. They were sophisticated marine hunters with advanced hydrodynamic adaptations and complex social behaviors. Other marine reptile lineages experimented with different ecological strategies. The ichthyosaurs, dolphin-like reptiles that had first appeared during the Triassic period, continued to diversify during the Jurassic, with some species developing echolocation capabilities similar to modern dolphins and whales. The pliosaurs, short-necked relatives of the plesiosaurs, evolved into some of the most powerful marine predators ever to exist, with skulls that could exceed 6 feet in length and bite forces that rivaled those of the largest dinosaurs. The success of these marine reptile communities had important implications for terrestrial ecosystems as well. Many of these oceanic giants were capable of venturing into coastal waters and river systems to hunt, creating evolutionary pressures for terrestrial animals to develop new defensive strategies. Some of the most sophisticated group behaviors and anti-predator adaptations seen in Jurassic dinosaur communities may have evolved in response to threats from marine superpredators. The expanding marine ecosystems also created new opportunities for the evolution of flying reptiles. The pterosaurs, which had first appeared during the Triassic period, began to diversify rapidly during the Jurassic, as the expanding network of seaways and coastal environments provided ideal hunting grounds for aerial predators. Some pterosaur lineages developed wingspans that exceeded 20 feet, making them among the largest flying animals ever to exist. These giant pterosaurs weren't just scaled-up versions of smaller species. They had evolved sophisticated flight adaptations that included hollow bones, advanced wing membrane structures, and complex muscle arrangements that allowed them to soar efficiently over vast distances. Their success demonstrated that the airspace above Earth's fragmenting continents was becoming an increasingly important ecological frontier. As the Middle Jurassic period progressed, the effects of continental fragmentation were becoming visible in virtually every aspect of Earth's biological systems. The climate was becoming more varied and regionally distinct as different continental fragments drifted into different latitudinal zones and developed their own weather patterns. Ocean circulation was becoming more complex as new seaways created additional pathways for heat and moisture transport. Most importantly, The biological communities on different continental fragments were beginning to develop their own distinct characteristics. The process wasn't uniform or predictable. Some continental fragments remained connected by land bridges for millions of years after initial rifting began, allowing continued biological exchange even as overall supercontinent structure broke down. Other regions separated quickly and completely, leading to rapid evolutionary divergence. The result was a complex mosaic of connected and isolated populations that created unprecedented opportunities for evolutionary experimentation. In some regions, the continued connection between continental fragments allowed for the development of transcontinental migration routes that supported some of the largest animal populations in Earth's history. Fossil evidence suggests that some dinosaur species maintained continent-spanning ranges well into the Middle Jurassic period, with individual populations migrating thousands of miles following seasonal food resources. In other areas, the rapid development of marine barriers created island-like environments where small populations became isolated and began evolving in directions that would have been impossible in larger, more connected populations. Some of these isolated communities developed into highly specialized ecosystems with unique species found nowhere else on Earth. The mammals that had survived in the shadows of the giant reptiles were also beginning to diversify in response to the changing conditions. While they remained relatively small compared to the dominant dinosaurs, they were developing increasingly sophisticated adaptations that allowed them to exploit ecological niches that were unavailable to larger animals. Some mammalian lineages were experimenting with arboreal lifestyles in the increasingly complex forest canopies that were developing in many regions. Others were developing semi-aquatic adaptations that allowed them to exploit the expanding network of freshwater environments created by continental rifting. Still others were evolving specialized diets and behaviors that allowed them to coexist with dinosaur communities without direct competition. The success of these early mammalian experiments was laying the groundwork for the evolutionary explosion that would occur much later, after the extinction of the dinosaurs. But even during the Jurassic period, mammals were demonstrating the adaptability and innovation that would eventually make them one of the most successful vertebrate groups in Earth's history. The insect communities that form the foundation of many terrestrial food webs were also undergoing dramatic changes during this period. The evolution of flowering plants created new food resources and habitat types that insects could exploit. Some insect lineages developed increasingly sophisticated relationships with plants, including the early stages of the complex pollination partnerships that would eventually become so important to terrestrial ecosystems. Other insect groups were evolving in response to the changing vertebrate communities. The success of large herbivorous dinosaurs created opportunities for insects that could exploit the dung, dead skin, and other organic materials produced by these giants. Some insects developed specialized relationships with particular dinosaur species, living as commensals or even parasites on their reptilian hosts. The diversity and complexity of insect communities during the Middle Jurassic period was probably comparable to modern levels, though the specific species and ecological relationships were very different. These communities provided crucial ecosystem services, including pollination, decomposition, and nutrient cycling that supported the complex food webs that were developing across the fragmenting supercontinent. As we move toward the late Jurassic period, around 150 million years ago, the effects of Pangea's breakup were accelerating. The Atlantic Ocean was widening rapidly, creating an increasingly formidable barrier between the Americas and Africa-Europe. Other rift systems were beginning to separate additional continental fragments, including the early stages of the rifting that would eventually separate Antarctica from South America and Australia. The biological consequences of this accelerating fragmentation were becoming increasingly apparent. The dinosaur faunas of different continental regions were diverging rapidly, with many species now found only in specific geographic areas. The plant communities were also becoming more regionalized, with different continental fragments developing their own characteristic vegetation types. But perhaps most significantly, the process of continental drift was beginning to create the geographic framework that would influence evolution for the rest of Earth's history. The separated continents would continue drifting apart, carrying with them the biological heritage of Pangea, but developing it in new and unique directions. The stage was being set for the incredible diversity of ecosystems that would characterize the later Mesozoic and Cenozoic eras. The world that was emerging from Pangea's dissolution was more complex, more varied, and in many ways more dynamic than the supercontinent that had preceded it. The extreme environmental conditions that had characterized Pangea during its peak extent were giving way to a more moderate but more diverse set of climate patterns. The ecosystems that had been adapted to continental scale uniformity were being replaced by regionally distinct communities adapted to local conditions. This transformation wasn't just a matter of geographic rearrangement. It represented a fundamental shift in how evolution operated on Earth. Instead of the continent-wide evolutionary pressures that had characterized the Pangean world, life was now responding to a complex mosaic of local and regional pressures that varied significantly from place to place. The result was an explosion of biological diversity that would continue accelerating throughout the remainder of the Mesozoic era. The relatively simple ecosystems of early Pangea were giving way to complex interconnected webs of species that would eventually support levels of biodiversity that may have exceeded even modern levels. As the late Jurassic period approached and Pangea's fragmentation continued, the biological world was poised for another period of rapid innovation and diversification. The foundations had been laid for the Golden Age of Dinosaur evolution, the rise of complex marine ecosystems, and the early stages of the evolutionary processes that would eventually lead to the modern world. The story of life during Pangea's existence and breakup reveals something profound about the relationship between geography and evolution. The extreme conditions created by supercontinent assembly had pushed life to develop innovations and adaptations that might never have evolved under more moderate conditions. But the fragmentation of that supercontinent created opportunities for those innovations to be tested and refined in new contexts, leading to levels of diversity and complexity that continue to influence Earth's biological systems today. The ancient supercontinent that had dominated our planet for more than 160 million years was nearing the end of its existence, but its biological legacy was just beginning to unfold in ways that would shape life on Earth for hundreds of millions of years to come. The extreme world of Pangea had served as both a crucible and a launching pad for some of the most successful evolutionary experiments in our planet's history, and those experiments were about to enter their most spectacular phase. The geological forces that would ultimately complete Pangea's transformation into the modern world were gaining momentum as we approach the late Jurassic period, around 150 million years ago. But what was happening beneath the surface of these separating continents was even more remarkable than the dramatic rifting we could observe from above. Deep within Earth's mantle, the same convection currents that had orchestrated the supercontinent's assembly were now choreographing an even more complex dance of creation and destruction. Picture massive plumes of superheated rock rising from the boundary between Earth's core and mantle, travelling nearly 2,000 miles through the planet's interior before reaching the base of the continental crust. These weren't gentle, gradual processes. These were thermal hurricanes of molten rock, each one carrying enough energy to power human civilization for millions of years. When these plumes finally reached the surface, they didn't just create ordinary volcanic eruptions. They generated hotspot volcanism on a scale that dwarfed anything in recorded human history. The Hawaiian island chain provides a modern example of hotspot volcanism, but during the late Jurassic period, similar processes were operating simultaneously across multiple locations within the fragmenting supercontinent. Imagine not just one Hawaii, but dozens of them, each one punching holes through continental crust that was already under tremendous stress from the rifting process. The result was a period of volcanic activity so intense it fundamentally altered the chemistry of Earth's oceans and atmosphere. These volcanic systems weren't just randomly distributed across the breaking supercontinent. They appeared to follow patterns that revealed something profound about the deep structure of our planet. The hotspots that were driving much of the late Jurassic volcanism were positioned along lines that corresponded to ancient zones of weakness in Earth's crust, regions where previous episodes of continental assembly and breakup had left permanent scars in the geological record. The interaction between these deep mantle processes and the ongoing continental rifting created feedback loops that accelerated the pace of Pangea's dissolution. As volcanic activity weakened the crust along rift zones, it made it easier for tectonic forces to pull the continents apart. At the same time, the stretching and thinning of the crust created pathways for magma to reach the surface more easily, intensifying the volcanic activity. For the biological communities that had been adapting to the gradually changing conditions of the Middle Jurassic period, this acceleration in geological processes created new challenges and opportunities. The increased volcanic activity pumped enormous quantities of carbon dioxide and other gases into the atmosphere, creating a greenhouse effect that pushed global temperatures even higher than the already warm conditions that had characterized most of the Mesozoic era. But the effects weren't uniformly distributed across the planet. The positioning of volcanic hotspots and the patterns of continental drift meant that different regions experienced very different environmental changes. Some areas became significantly warmer and more humid, creating tropical conditions that extended much farther from the equator than they do today. Other regions experienced more complex changes, with shifting wind patterns and ocean currents, creating new climate zones that had no modern equivalent. The dinosaur communities that had been flourishing during the Middle Jurassic period found themselves in a world that was changing more rapidly than at any time since the recovery from the Great Dying. But rather than struggling to adapt to these changes, many dinosaur lineages seemed to thrive in the new conditions. The late Jurassic period would prove to be the golden age of dinosaur diversity, with more species and a greater variety of ecological strategies than had ever existed before or would exist again. The sauropods, those gentle giants that had been growing steadily larger throughout the Jurassic period, reached their ultimate expression during this time. Diplodocus, with its incredibly long neck and tail, could reach lengths of nearly 90 feet while maintaining the relatively lightweight build that had made sauropods so successful. Brachiosaurus, with its upright posture and massive forelegs, could reach heights of over 40 feet, allowing it to browse on vegetation that was completely inaccessible to other herbivores. But perhaps the most remarkable aspect of late Jurassic sauropod evolution wasn't just their size, it was their diversity. Different species had evolved radically, different body plans and feeding strategies, allowing multiple giant herbivores to coexist in the same ecosystems without direct competition. Some species were optimized for ground-level feeding, using their long necks to sweep across vast areas of low-growing vegetation. Others were specialized for high browsing, able to strip leaves from the tops of the tallest trees. The success of these diverse sauropod communities created opportunities for equally diverse predator communities to evolve. Allosaurus, the apex predator of late Jurassic North America, represented a completely different approach to carnivorous dinosaur design than the earlier theropods of the Triassic period. These weren't just larger versions of primitive predators. They were sophisticated hunters with advanced sensory systems, powerful limbs capable of bringing down prey many times their own weight, and possibly even complex social behaviours that allowed them to coordinate attacks on the largest herbivores. The arms race between predator and prey during the late Jurassic period drove innovations that pushed the boundaries of what was possible in vertebrate biology. Some herbivorous dinosaurs developed defensive adaptations that seem almost impossible by modern standards. Stegosaurus, with its distinctive rows of plates and spiked tail, wasn't just passively armoured. Recent research suggests that its plates may have been capable of changing colour, allowing these animals to communicate with each other and possibly even to intimidate predators through visual displays. Other herbivorous species developed different defensive strategies. Some evolved incredibly thick skin and bony armour that could deflect the attacks of even the largest predators. Others relied on speed and agility, developing long, powerful legs that could carry them away from danger at speeds that would be impressive even by modern mammalian standards. But perhaps the most significant development during the late Jurassic period wasn't related to the giant dinosaurs that dominate our imagination. It was the continuing evolution of the smaller, more agile dinosaur lineages that were experimenting with powered flight. By 150 million years ago, these experiments had produced Archaeopteryx, a creature that was unmistakably both dinosaur and bird. Archaeopteryx wasn't a primitive, clumsy flyer struggling to get off the ground. Recent analysis of its feathers and bone structure suggests it was a capable, if specialized, flying animal that had mastered the complex aerodynamics required for powered flight. More importantly, it represented just one branch of a much larger evolutionary radiation that was occurring among small theropod dinosaurs during this period. The forests of the late Jurassic period were filled with feathered dinosaurs of various sizes and capabilities. Some were primarily ground-dwelling predators that used their feathers for insulation and display. Others were developing increasingly sophisticated gliding abilities that allowed them to move through forest canopies with remarkable agility. Still others were experimenting with the powered flight capabilities that would eventually make their descendants the most successful vertebrates on Earth. The plant communities that supported these diverse animal populations were also reaching new levels of complexity during the late Jurassic period. The flowering plants that had first appeared during the Middle Jurassic were diversifying rapidly, though they were still far from the dominant vegetation type they would eventually become. The gymnosperm forests that form the backbone of most terrestrial ecosystems were achieving levels of structural complexity that may have exceeded modern rainforests. Picture forests, where the canopy layer extended over 200 feet above the ground, supported by massive conifer trees with trunks that could exceed 10 feet in diameter. Below this canopy, multiple layers of smaller trees, tree ferns, and other plants created a three-dimensional habitat structure that provided ecological niches for an incredible diversity of animal species. The forest floor was carpeted with ferns, mosses, and other low-growing plants that thrived in the filtered light that penetrated through the dense canopy above. These forest ecosystems weren't just vertically complex. They were also incredibly diverse in terms of the species they supported. Different plant communities had evolved in response to the varying climate conditions created by the ongoing continental drift, and each community supported its own characteristic assemblage of animal species. The result was a patchwork of ecosystems across the fragmenting supercontinent, each one a unique experiment in biological organization. The marine ecosystems surrounding the separating continents were experiencing equally dramatic developments. The Atlantic Ocean, which had begun as a narrow rift valley during the early complex marine food webs. But this wasn't just a smaller version of modern ocean ecosystems. The warm, shallow conditions Jurassic was now a substantial body of water that characterized much of the late Jurassic Atlantic. It created opportunities for marine life that don't exist in today's deeper, colder oceans. Coral reefs during the late Jurassic period were more extensive and diverse than at any other time in Earth's history. These weren't built by the same types of corals we see today, but by rudists, bizarre clam-like organisms that could grow to enormous sizes and create reef structures that rivaled modern coral reefs in their complexity and biological diversity. Some rudist reefs extended for hundreds of miles along continental margins, creating habitat for marine communities that included species found nowhere else. The marine reptiles that dominated these reef ecosystems were equally remarkable. Plesiosaurs had evolved into forms that were perfectly adapted to life in shallow reef-rich environments. Some species developed incredibly long necks that allowed them to probe into crevices and caves in search of prey. Others evolved more compact builds, optimized for maneuvering through the complex, three-dimensional structure of the reefs themselves. The success of these marine ecosystems had important implications for the global carbon cycle and climate system. The extensive coral reefs and other carbonate-producing organisms were removing enormous quantities of carbon dioxide from the atmosphere and locking it away in limestone deposits. This biological carbon sequestration helped to moderate the greenhouse effects of the increased volcanic activity, creating a complex feedback system that influenced climate patterns across the planet. But the most remarkable aspect of late Jurassic marine ecosystems wasn't their individual components. It was the way they were becoming integrated with terrestrial ecosystems in unprecedented ways. The fragmenting continents created thousands of miles of new coastline, and these coastal zones became centers of biological innovation where marine and terrestrial species interacted in ways that had been impossible during Pangea's peak extent. Some dinosaur species were developing semi-aquatic lifestyles, spending significant portions of their time in coastal waters, feeding on marine vegetation and small marine animals. Fossil evidence suggests that some large theropods were capable swimmers that could hunt in both terrestrial and marine environments. These amphibious predators created evolutionary pressures for marine organisms to develop new defensive strategies, while also opening up new ecological niches for species that could exploit both environments. The pterosaurs that soared above these coastal ecosystems were also developing increasingly sophisticated relationships with marine environments. Some species evolved specialized feeding adaptations that allowed them to plunge into the water to catch fish, similar to modern pelicans. Others developed filter feeding capabilities that allowed them to strain small organisms from the water while flying just above the surface. The integration of marine and terrestrial ecosystems during the late Jurassic period created opportunities for nutrient cycling and energy transfer that operated on continental scales. Seabirds, marine reptiles, and other animals that moved between marine and terrestrial environments transported nutrients from the productive coastal waters to inland ecosystems, fertilizing terrestrial plant communities and supporting higher levels of biological productivity than would have been possible otherwise. As the late Jurassic period progressed toward its end around 145 million years ago, the effects of Pangea's breakup were becoming irreversible. The Atlantic Ocean was wide enough to prevent any possibility of the American and African-European continental masses reuniting. Similar rifting processes were beginning to separate other continental fragments, including the early stages of the breakup that would eventually isolate Antarctica from the other southern continents. The biological communities that had evolved during the late Jurassic period represented the culmination of more than 200 million years of evolution on and around a supercontinent. The extreme conditions that had characterized Pangea's assembly and peak extent had pushed life to develop innovations and adaptations that might never have evolved under more moderate circumstances. But the fragmentation of the supercontinent had created opportunities for those innovations to be tested and refined in new contexts, leading to levels of diversity and complexity that were unprecedented in Earth's history. The transition from the Jurassic to the Cretaceous period around 145 million years ago, marked not just a change in geological time periods, but a fundamental shift in how Earth's biological systems operated. The world that was emerging from Pangea's dissolution was more geographically complex, more climatically diverse, and more biologically innovative than the supercontinent that had preceded it. The dinosaur communities that would dominate the Cretaceous period were already taking shape during the latest Jurassic. New lineages were appearing that would eventually produce some of the most famous dinosaurs in popular culture, including the tyrannosaurs, the advanced hadrosaurs, and the armored ankylosaurs. But these Cretaceous dinosaurs would evolve in a world that was fundamentally different from the one their Jurassic ancestors had inhabited. The continued fragmentation of Pangaea during the early Cretaceous period created even more opportunities for regional specialization and evolutionary divergence. The South American dinosaur faunas that evolved during this period were dramatically different from contemporary communities in North America, Africa, or Asia. Each continental fragment was becoming its own evolutionary laboratory, testing different solutions to the challenges of life in an increasingly diverse and complex world. The flowering plants that had begun their evolutionary radiation during the Jurassic period were poised for an explosive expansion during the Cretaceous. The warm, humid climate conditions created by continued continental drift provided ideal conditions for angiosperm diversification. By the middle of the Cretaceous period, flowering plants would transform terrestrial ecosystems in ways that were as revolutionary as any change in Earth's biological history. The co-evolution of flowering plants and their animal pollinators would create entirely new categories of ecological relationship and drive levels of biological diversity that exceeded anything that had existed during the Pangean world. The simple gymnosperm forests that had dominated terrestrial ecosystems for hundreds of millions of years would be replaced by complex angiosperm communities that supported intricate webs of interdependent species. The marine ecosystems that had flourished in the warm, shallow seas of the late Jurassic period were also poised for continued expansion and diversification. The Cretaceous period would see the evolution of some of the largest and most sophisticated marine reptiles in Earth's history, including massive mosasaurs that could exceed 50 feet in length and plesiosaurs with necks longer than their entire bodies. But perhaps most significantly, the biological innovations that had been forged during Pangea's existence were about to be tested under entirely new conditions. The separated continents would continue drifting apart, eventually creating the geographic framework that would influence evolution for the remainder of Earth's history. The extreme world of Pangaea had served as both a crucible and a launching pad for evolutionary processes that would shape life on our planet for hundreds of millions of years to come. The story of life during Pangaea reveals something profound about the relationship between environmental challenge and biological innovation. When conditions are stable and moderate, evolution tends to produce gradual refinements of existing strategies. But when environments become extreme and unpredictable, life responds with bursts of creativity that can fundamentally reshape the biological world. The supercontinent that had dominated our planet for more than 160 million years was nearing the end of its existence, but the biological legacy of its extreme conditions was just beginning to unfold. The innovations and adaptations that had been tested in the crucible of Pangea's harsh interior, its mega monsoon climate, and its recovery from the greatest mass extinction in Earth's history would provide the foundation for all subsequent evolution on our planet. As we stand at the threshold of the Cretaceous period and witness the final stages of Pangea's transformation, we can see that we're observing one of the most important transitions in the history of life on Earth. The world that would emerge from the supercontinent's dissolution would be more diverse, more complex, and more dynamic than anything that had come before, but it would be built on the remarkable biological toolkit that had been assembled during the extraordinary era when all of Earth's land was united as one. The profound transformation we're witnessing as Pangia dissolves into separate continents represents something far more significant than simple geographical rearrangement. We're observing the birth of biogeographic isolation on a scale that would fundamentally alter the trajectory of evolution for the remainder of Earth's history. As these ancient landmasses drifted apart, they carried with them not just rocks and minerals, but entire evolutionary legacies that would unfold in dramatically different directions. Picture what was happening to the mammalian lineages during this critical transition period. These small warm-blooded creatures had spent the entire Mesozoic era living in the shadows of their reptilian contemporaries, developing sophisticated adaptations while remaining relatively inconspicuous members of most ecosystems. But as continental separation accelerated, these mammalian populations found themselves isolated on different land masses, setting the stage for evolutionary experiments that would eventually reshape terrestrial life. On the fragmenting northern continents, mammalian communities began developing along pathways that emphasized intelligence, social cooperation, and behavioral flexibility. The challenging seasonal variations and complex forest environments of these regions favored mammals that could learn, adapt, and modify their behaviors in response to changing conditions. Some lineages began developing enlarged brain cases and more complex neural organizations, early steps toward the cognitive capabilities that would later characterize advanced mammals. Meanwhile, the southern continental fragments were fostering very different mammalian evolutionary strategies. The generally warmer, more stable climate conditions in these regions allowed for the development of larger body sizes and more specialized ecological roles. Some southern mammalian lineages began experimenting with dietary strategies that brought them into more direct competition with reptilian herbivores, developing the powerful jaw muscles and specialized teeth that would eventually allow them to exploit food resources that had been dominated by dinosaurs for over 100 million years. But perhaps the most remarkable aspect of this mammalian diversification was how different continental fragments began developing their own signature approaches to placental reproduction and infant care. The isolation of breeding populations allowed for experimentation with different strategies for nourishing and protecting young mammals during their extended development periods. Some regions saw the evolution of mammals with longer gestation periods and more advanced offspring, while others developed elaborate pouch systems and extended parental care behaviors. The plant communities that formed the foundation of these evolving ecosystems were undergoing equally dramatic transformations. The flowering plants that had begun their evolutionary radiation during the Jurassic period were now diversifying at unprecedented rates, but they were doing so independently on different continental fragments. This geographic isolation was creating opportunities for parallel evolution on a scale that had never existed before in Earth's history. Consider what was happening to the early rose and magnolia lineages during this period. On the northern continents, these flowering plants were evolving in response to increasingly seasonal climate patterns and the browsing pressure created by diverse dinosaur communities. They developed sophisticated chemical defenses, complex flower structures for attracting specific pollinators, and seed dispersal mechanisms that could function effectively in the dense forest environments that characterize these regions. The same basic plant lineages on southern continents were evolving very different solutions to the challenges of angiosperm life. The warmer, more stable conditions allowed for the development of larger, more conspicuous flowers and fruits, while the different herbivore communities created selection pressures for entirely different defensive strategies. Some southern flowering plants began developing mutualistic relationships with specific animal species, creating the beginnings of the complex co-evolutionary partnerships that would later characterize tropical ecosystems. The insects that served as pollinators for these diversifying plant communities were themselves undergoing explosive evolutionary radiation. The geographic isolation of plant populations created opportunities for insect species to develop highly specialized relationships with particular flowering plant lineages. On different continents, the same basic insect groups were evolving different approaches to nectar feeding, pollen collection, and flower recognition. The early bees that were emerging during this period provide a fascinating example of parallel evolution in action. On northern continents, bee lineages were developing social behaviors and colony organization strategies that allowed them to exploit the brief but intense flowering seasons characteristic of more seasonal climates. Southern bee communities were evolving different approaches that emphasized individual foraging efficiency and the ability to exploit the more consistent but diverse flowering resources available in less seasonal environments. These differences in pollinator behavior were driving corresponding differences in flower evolution on different continents. Northern flowering plants were developing synchronous blooming strategies and flower structures optimized for efficient pollination during brief seasonal windows. Southern plants were evolving more diverse flowering schedules and flower forms that could attract and reward the different types of pollinators that were available in their regions. The marine ecosystems surrounding these separating continents were experiencing their own patterns of biogeographic diversification. As new ocean basins formed and existing seaways deepened, they created barriers to the movement of marine organisms that were just as effective as the land barriers that were isolating terrestrial species. Marine communities that had been connected across the Tethys Ocean and early Atlantic were becoming increasingly isolated and beginning to evolve in different directions. The marine reptile communities provide some of the most dramatic examples of this oceanic biogeographic evolution. Plesiosaur populations that became isolated in different ocean basins began developing very different body plans and feeding strategies. Atlantic plesiosaurs were evolving increasingly long necks and specialized feeding adaptations for life in the relatively shallow reef-rich environments that characterized the early Atlantic Ocean. Pacific plesiosaur lineages, living in the deeper, more open waters of the vast Panthalassa Ocean, were developing different adaptations that emphasized speed, endurance, and the ability to hunt in open water environments. Some Pacific species were evolving the echolocation capabilities and advanced hydrodynamic features that would allow them to compete effectively with the sophisticated marine reptiles that were already established in these oceanic environments. The ichthyosaurs, those dolphin-like marine reptiles, were experiencing similar patterns of geographic diversification. Different populations were developing specialized adaptations for hunting in the specific marine environments of their respective ocean basins. Some were becoming deep water specialists, capable of diving to extraordinary depths in pursuit of squid and other soft-bodied prey. Others were evolving as shallow water generalists that could exploit the diverse food resources available in coastal and reef environments. But the most significant aspect of this marine diversification wasn't just the evolution of different species in different ocean basins. It was the way these isolated marine communities were beginning to develop their own characteristic ecosystem structures and energy flow patterns. Different oceanic regions were essentially experimenting with different approaches to marine ecosystem organization, each one testing various solutions to the fundamental challenges of life in aquatic environments. The pterosaurs that soared above these diversifying marine and terrestrial ecosystems were also experiencing the effects of biogeographic isolation. Different continental regions were developing their own characteristic pterosaur faunas, each adapted to the specific flying conditions and food resources available in their respective areas. Northern pterosaur communities were evolving sophisticated soaring adaptations that allowed them to exploit the thermal updrafts created by the increasingly complex topography of fragmenting continents. Southern pterosaur lineages were developing different flight strategies optimized for the generally calmer, more stable atmospheric conditions that characterized lower latitudes. Some were evolving filter-feeding capabilities that allowed them to exploit the rich plankton communities of warm, shallow seas. Others were developing powered flight capabilities that surpassed even modern birds in their efficiency and maneuverability. The diversity of pterosaur ecological strategies during this period was truly remarkable. Some species were developing wingspans that exceeded 30 feet, making them among the largest flying animals ever to exist. These giants were capable of soaring for thousands of miles without landing, exploiting wind patterns and thermal currents with a sophistication that modern glider pilots can only dream of achieving. Other pterosaur lineages were exploring the opposite extreme, evolving into small, highly maneuverable forms that could navigate through dense forest canopies and exploit ecological niches that were unavailable to larger flying animals. These forest pterosaurs were developing advanced visual systems and rapid response flight capabilities that allowed them to hunt insects and small vertebrates in the complex three-dimensional environments of late Jurassic and early Cretaceous forests. The success of diverse pterosaur communities was creating new categories of ecological interaction that had never existed before. Some large pterosaurs were developing predatory relationships with small dinosaurs, while others were evolving as specialized scavengers that could exploit carcasses that were inaccessible to ground-based scavengers. Still others were becoming important seed dispersers, carrying fruits and seeds across vast distances and facilitating plant colonization of newly formed habitats. As the Cretaceous period began around 145 million years ago, the biological world that was emerging from Pangea's dissolution was more geographically complex and evolutionarily dynamic than anything that had existed during the supercontinent's unified existence. The extreme environmental conditions that had characterized Pangaea during its peak extent had been replaced by a diverse mosaic of regional climates and ecosystems, each one fostering its own unique evolutionary experiments. The dinosaur communities that would dominate the Cretaceous period were already showing clear signs of biogeographic differentiation. The tyrannosaur lineages that were evolving in northern regions were developing very different characteristics from the abelosaurid predators that were emerging on southern continents. Each group was adapting to the specific prey communities and environmental conditions of their respective regions, creating parallel evolution in large predatory dinosaurs that would eventually produce some of the most formidable land predators in Earth's history. The herbivorous dinosaur communities were showing even more dramatic patterns of geographic specialization. The hadrosaurs that were beginning to diversify in northern regions were developing sophisticated dental adaptations for processing the tough, fibrous vegetation that characterized seasonal forest environments. Southern herbivorous dinosaurs were evolving different feeding strategies optimized for the broader variety of plant types available in less seasonal climates. The armored dinosaurs that were emerging during this period were also showing clear biogeographic patterns in their evolution. Northern ankylosaurs were developing heavy, club-like tail weapons and extensive body armor that suggested they faced significant predation pressure from large theropods. Southern armored dinosaurs were evolving different defensive strategies that emphasized speed and agility rather than passive protection, reflecting the different predator communities they encountered in their respective regions. But perhaps the most significant development during the early Cretaceous period was the explosive radiation of flowering plants that was beginning to transform terrestrial ecosystems across all continental fragments. The angiosperms that had been minor components of Jurassic plant communities were rapidly diversifying and beginning to dominate many terrestrial environments. This flowering plant revolution wasn't happening uniformly across the globe, however. Different continental regions were developing their own characteristic angiosperm communities, each adapted to local climate conditions and ecological relationships. The co-evolution of flowering plants and their animal partners was creating feedback loops that accelerated the pace of evolutionary change in both groups. As plants developed more sophisticated flowers to attract specific pollinators, the insects and other animals that visited these flowers evolved increasingly specialized adaptations for nectar feeding and pollen collection. This co-evolutionary process was creating levels of biological diversity that exceeded anything that had existed during the gymnosperm-dominated ecosystems of earlier periods. The early Cretaceous period was also witnessing the emergence of the first grasslands, though these were very different from modern grass-dominated ecosystems. The early grasses were small, relatively inconspicuous plants that grew in disturbed areas and forest clearings, but they possessed several characteristics that would eventually make them incredibly successful. Rapid growth rates, efficient nutrient uptake, and the ability to recover quickly from grazing damage. The appearance of grasses during the early Cretaceous period created new opportunities for herbivorous animals to exploit food resources that had been largely unavailable during previous periods. Some dinosaur lineages began developing specialized dental adaptations for processing grass and other small, tough plant materials. These early grass-eating dinosaurs were the pioneers of grazing strategies that would eventually be perfected by mammals during the Cenozoic era. The marine ecosystems of the early Cretaceous period were experiencing equally dramatic changes in response to continued continental drift and the evolution of new marine food webs. The Atlantic Ocean was now large enough to support its own characteristic marine communities, distinct from both the Pacific fauna and the remnants of the Tethyan communities that persisted in the Mediterranean region. The rudest reefs that had been so successful during the late Jurassic period were reaching their maximum extent during the early Cretaceous, creating some of the most extensive reef systems in Earth's history. These reefs supported marine communities of incredible diversity, including specialized fish, marine reptiles, and invertebrate communities that were found nowhere else in the world's oceans. And so, as we drift back through the vast corridors of deep time to our present moment, we can see that we've been witnesses to one of the most extraordinary chapters in Earth's 4.5 billion year story. Tonight, we've walked across a world that existed on scales almost impossible to imagine, where life itself was forged in conditions so extreme they pushed evolution to create solutions that still echo through every ecosystem on our planet today. From Pangea's formation, in that slow-motion continental collision, through the mega-monsoon systems that painted entire continents with seasonal extremes, to the great dying that nearly erased life from Earth, and finally to the supercontinent's dissolution that scattered the seeds of modern biodiversity across separated land masses. We've seen how our planet's most ambitious geological experiment shaped the very foundations of life as we know it. The next time you step outside, remember that the ground beneath your feet carries within it the memory of that ancient supercontinent, and the air you breathe connects you to atmospheric systems that began evolving when all of Earth's land was one. What other deep time mysteries would you like us to explore together on future journeys through our planet's incredible past?